Hello everyone, my name is Xiangpeng. I'm a PhD student in the Microelectronics Lab of University of Glasgow. It's my honor to share my research at ISCAS conference. The topic of my paper is a delay-based neuromorphic processor for arrhythmia detection. Here is the outline of my presentation. First of all, I will talk about the background of my research. In this project, we applied the hardware-based neuromorphic model on an automatic ECG classification task. Therefore, the background of neuromorphic computing and automatic ECG classification will be provided separately. Later on, in the introduction, I will introduce the motivation of this paper, why we want to apply neuromorphic computing on automatic ECG classification, and what is the contribution of this paper. After that, in the modeling session, we will discuss more technical details about this project, and including the principle and some important parameters. Finally, this model will be evaluated by the ECG data, and the result will be also provided. To begin with the background, I will first discuss the conventional methods for arrhythmia detection. This figure summarizes the commonly used procedures for automatic ECG classification. First of all, we will have an electrode on the patient's body. The electrode will collect electricity around the heart. This electrical signal contains rich information about the heart activity, which can be used for diagnosis of cardiovascular disease. And after the sensor, we need a phone-end circuit to adjust the signal and improve the signal-to-noise ratio. And the ADC will convert the analog signal to the digital system, because in the digital system we can do lots of more complicated operations. For example, the heartbeat segmentation and feature extraction based on the QRS complex of ECG. The feature metric will be used in the testing or training in the machine learning. Based on this commonly used pathway, previous research investigated lots of different combinations of feature metric and machine learning algorithm, and they got very high accuracy and sensitivity. Here, we need to note that after ADC, all of these operations are based on the digital system. Another background of this paper is neuromorphic engineering. We all know the artificial neural network is a bio-inspired algorithm to process the data for the machine learning tasks. And the purpose of neuromorphic computing is to develop the hardware that can mimic biological neural network for signal processing. Because it has been reported that for the tasks like prediction and classification or recognition, our brain is in several orders in magnitude more power efficient than the digital system, because our brain is a pure analog system. So this is the aim of the neuromorphic engineering. We want to reduce the power consumption and improve the signal processing rate for such a task. And the delay-based reservoir computing is one of the candidates to be implemented by the hardware. It was first proposed in 2011. It's a special type of reservoir computing, but different from the conventional reservoir computing. The DRC replaced the randomly generated connection in the reservoir with a delay coupled node. This is special because it strongly facilitates the physical implementation of this kind of network and require less components. In this paper, we propose a neuromorphic processor for ECG signal processing. This is the conceptual figure of our project. We want to have a pure analog neuromorphic processor to receive the ECG signal. And this neuromorphic processor is based on the delay-based reservoir computing. Here is the diagram of a delay-based reservoir computing. We expected all of these procedures are analog, which is in line with the idea of neuromorphic computing. The contribution of this paper is we provide a fundamental modeling of this delay-based reservoir computing, and we didn't use the intensive digital operation. For example, the commonly used signal segmentation and feature extraction in the conventional method of ECG classification, and this model was also evaluated by the ECG data. We need to decide a delay-based reservoir specifically for the ECG signal processing. Here is the typological structure of the DRC, and here is the simulation model. In conventional RC, the reservoir is subjected to this equation. The node state at each step is depends on the previous node state and the current input as well as the activation function. The delay-based RC is different. It is subjected to a delay differential equation. In this kind of system, the ECG signal should be multiplied by the mask, and the summation of the mask input and the delay feedback will be taken and sent to the nonlinear nodes. If we sampled the nonlinear nodes with a certain sampling rate theta, we will have the node state, and this node state will be used in the post-processing to calculate output. We design the simulation model according to the typological structure. And this is the step response of this circuit design. The step response is important because if we have a sampling rate theta smaller than this t, the delay-based reservoir will generate a complex dynamic which is similar to the reservoir in the conventional reservoir computing. And also, this is the nonlinear transformation for the input signal. In addition, the fading memory created by the delayed feedback retains the previous information of previous input in the reservoir computing. Making full use of the fading memories allows the network to keep the whole ECG morphology in the network. This is why we don't need feature extraction and signal segmentation in our design. In this simulation, the reservoir behavior can be also investigated. This figure shows the signal at different stages of the delay-based reservoir computing. The purpose of the mask is that we want to create a time multiplexing for the input ECG signal. If we look at this figure, the input ECG sample is multiplied by a mask and expanded to a square wave. This square wave will result in a complex dynamic at output. In this figure, the red dot represents the node state at the output, and the node state matrix will be the high-dimensional representation of the input ECG signal. We confirm that the time multiplexing of the input creates a dependency between the nodes. So the time multiplexing is important to map the input signal to the higher dimensional space. In order to validate the model, the task in this paper is to detect the rectangular ectopic bit from the ECG signal. This is the VEB and this is the normal ECG. And this diagram summarizes the procedure of chaining and testing. Before getting the node states, both chaining and testing follow the same procedure. We would need pre-processing for the ECG signal and then mask and then put them into the delay-based reservoir computing. After that, in the chaining step, the node state collected from the post-processing will be used to calculate the output weights by the ridge regression, and these output weights will be used to calculate the prediction result using the node state collecting from the testing data. A key operation is that we need to right shift the chaining label to the end of each heartbeat, because the node state collected at the end of each heartbeat contains the information of entire ECG. That's why we need to shift the location of the VEB to the end of the VEB as the chaining label. And here we have 4 standard criteria to evaluate the performance of the ECG classification. We will have sensitivity and positive prediction, specificity and accuracy. We choose 3 datasets from the MIT BIH database as testing datasets. The record 200, 203, 208 was selected because they contain lots of VEBs. Here is the description of the 3 datasets. Each dataset contains total 13 minutes ECG data, and the training dataset was randomly selected from the rest of the dataset in MIT BIH database. Finally, here is the result using the dataset. Ideally, a spike should appear at the end of each VEB. At the same time, the output should keep flat for the other type of ECG. This is because we set a spike at the end of every VEB in the training shifting labeled. These 3 figures shows the input ECG, the RC output, the result, and the ground truth. The ground truth is the location of VEB from the database. We can see that most of the VEB was captured by the DRC output. The overall performance metric is listed in this table. For these 3 datasets, we can obtain over 85% sensitivity, positive prediction, specificity, and accuracy. In conclusion, the proposed hardware-based model successfully processed the ECG signal, and we can recognize a certain type of heartbeat using this model. Also, according to the concept of neuromorphic engineering, we didn't use the digital operations such as signal segmentation and feature extraction. They are not desired in the analog system. Instead, we fully use the fading memory of the delay-based reservoir computing to preserve the feature and ECG methodology. Compared with the existing ECG classification algorithm, our model is a hardware-based architecture and is more achievable by using analog and or optical components, which has already been proved in the literature. And after that, this model was evaluated using the 3 datasets in the MIT BIH ISCAS database. The result shows that this hardware-based model can perform the neural network algorithm to capture a certain type of ECG data. In this paper, it's VEB type arrhythmia. The further development of this project will involve, first of all, we can evaluate this model using more comprehensive database to have more result. The second, we can design the pre- and post-processing circuit for our model to achieve pure analog computing. And we need to do lots of hardware experiment on it. More importantly, we need to evaluate the power consumption and processing rate, which is our ultimate goal. This is the reference for this presentation. Thank you for your listening.